Hi, I'm Clement.
Hi, I'm Michael.
I'm Miriam.
Welcome to our project, a model helicopter that hovers at a user's defined altitude using a proportional gain controller.
Our aim was to simulate how a real helicopter hovers. This meant we wanted to control the amount of lift by changing the pitch of our blades while spinning at a constant speed. We recognised the main challenges were building a reliable structure and generating sufficient measurable lift within the available time. We did this by making the design easier to build and improving its reliability, starting with the rotor.
The blades are angled so lift is generated by the helicopter, rising the helicopter side of the pivot up and lowering the end with the light sensor. The light sensor is against a graduated card from black to white, so as the light sensor moves vertically, the light level reading changes. We move the light sensor on the far end of the beam so it would move by a greater distance, resulting in larger changes of light levels, reducing the percentage uncertainty. We increase the length of the blade from the middle design to increase lift generated. Even though motor speed decreases due to increased drag, during the test we found that this is neglectable compared to the lift increase for larger blades. Applying the lift equation of potential flow theory mentioned in Moodle, we expected a 60% increase in lift at 20-degree angle of attack. This is our mechanism to change the pitch of the blades while they are spinning, using a second motor here. During initial testing, we discovered that with the original design, the shark tooth mechanism here sometimes didn't interlock correctly with the gears, causing inaccurate pitch control. So through multiple iterations, we improved the design by adding a back plate and rubber bands to ensure this mechanism worked more smoothly and more reliably, a key foundation that enabled us to develop a reliable software algorithm for hovering.
We made the structure and gearing of our helicopter more compact and simple to reduce mass and to avoid unnecessary complication. This includes balancing the secondary motor on these two axles here and also changing how the gearing worked for the pitch like this here to make it more compact as well. We also, as you can see here, improved the pivot from the original design on Moodle because we realised we needed the pivot to be well above the centre of mass of the system to ensure that it's passively stable. We calibrated the lift and pitch of the helicopter by doing different tests on it. So to calibrate lift, we added successive masses on here, and then we measured how much the light level changed for each mass added, and we then used that to calibrate the lift. And then we calibrated the pitch of the blades by using a phone with a protractor, online protractor on it, to work out what the angle of the pitch was at different angles of the motor here. This graph shows the amount of lift against the pitch angle for our helicopter. After a certain pitch angle, the lift significantly decreases, which is known as stalling in the principle of aerodynamic lift. This is because once the angle of attack is too large here, there is lots of large-scale flow separation and turbulent wake, which means that the lift decreases.
To test different configurations of the helicopter, initially we coded automated Python test scripts and plotted the data in matplotlib. But to improve our testing efficiency, we decided to build a graphical user interface with the Kiwi library here. As you can see, we have 5 buttons on the screen, and this allows us to change the configuration of the helicopter in real time. For example, we can increase or decrease the rotor speed, and increase or decrease the rotor pitch. Here is the logic of our real-time dashboard. To accelerate the development process and allow us to have more time to experiment with more exciting parts of the project, like the control algorithm, we decided to use ChatGPT to set up parts of the basic GUI template.
After achieving a reliable hardware design, we decided to challenge ourselves to implement an algorithm that hovers the helicopter at any height, which the user can set through the Graphical User Interface. Using the concepts of threading, we started to implement a PiD controller, starting with only the proportional gain. First, we need to get the current height of the helicopter through the light sensor. To compensate for vibrations, we apply a weighted moving average algorithm to smooth the light sensor readings. A target light sensor value is then set by the user through the GUI, and the difference between the current light sensor reading, which represents flight altitude, and the user's target altitude is calculated. The rotor pitch is then changed proportionally based on how far away we are from the target height. During demo day, our helicopter oscillated above and below the target height, as you can see here. But with about 30 minutes of extra tuning, we were able to get it to remain stable with just the proportional gain. A good extension to the project would be to explore implementing the derivative part of the PiD controller, representing vertical speed, to avoid overshooting the desired hover height initially. More advanced forms of data smoothing, like the Kalman filter, can also be explored.
Thank you.